Okay, now let's go into the lesson. We stopped last time talking about conduction, how heat can travel via contact from one object to another. This is going to be now convection. You guys have heard the word convection before. It's when probably through a convection oven, right? A convection oven basically is the same as your oven. The only difference is that it turns on a fan. So what's the big deal then? Well, convection, it circulates heat just a wee bit differently. So the question that I have here is, what if when a hot object warms a substance near it like it does in conduction, right? So, you know, like in your oven, you've got these hot coils inside your oven. They're touching the air next to them. And the only way to heat the food is if the air next to the coils heats the air next to that air, and then that air heats the air next to that, and so on and so forth until eventually that air next to the food gets warm, and then that air has to transfer the heat into the food. And my goodness, it can be a snail's pace if you've ever tried to heat a burrito in the oven compared to what it takes to do it on a microwave, right? Well, convection says, why don't we just sort of nip that process in the bud, and after I heat up some air next to this warm object, I'm going to move it away, like move that hot air next to the thing I want to heat up. And in its place, cold stuff will rush in, and then we'll heat that cold stuff up, get it out of the way, bring another piece of cold stuff in, and just keep the stuff circulating so that the heater element's always next to something that's cold compared to it. And the hot stuff moves over to heat up the rest of the place. That's convection. Now, I've shown a little picture here of a classic convection current. This happens in the old radiator heating systems that you see in big cities like New York's got these radiators everywhere. What they do is they're warm, they heat up the air next to it. Well, that air rises, and as it rises, it actually cools off, comes over here, then drops down. But you know, as it rises up, it leaves a void, so this cold air that's down here will rush up and fill it. And then as this thing falls, it'll also push some air up. But then while it's sitting here, this hot air will drop down and hit it and push it back up, and you get these nice currents. And so the warm stuff is circulating, and you heat up the room faster that way. The same thing happens with boiling water that you see here. The water that is heated, you guys know from last time, hotter water is less dense, so it floats. And as it floats, the cold stuff drops and then is touching the metal, which is touching the flame. So in that process, convection currents allow the water to heat faster. And that's just naturally what happens. This convection currents, well, do you remember when we talked about Santa Barbara and the sails and how the air over the desert would warm up and rise, and then the air over the ocean would sweep in? Now, I didn't tell you at the time, but that was really a convection current. You see, here's the sun. It's heating up. Well, the air over the town heats up, rises, cools off, but the air over the ocean comes over to where it can start heating up over the land. And then this air that already rose up will be cooling off again, and it'll drop down over the ocean, and the cycle repeats. But in the nighttime, the air over the water is warmer, so it rises. The air over the land cools, sweeps in to fill its place, and as the air circulates up, cools over, it'll come back down and fill up, and you get these currents. That's convection currents right there. It's responsible for those sea breezes that we talked about earlier. Now you might ask yourself, why does warm air rise? Well, because it expands. Now, things expand when they heat up, right? We get everything, all dimensions get bigger as the molecules jiggle and bounce each other further away. So as it expands, it becomes less dense, and that means that the weight of the air that air is displacing is greater than the weight of that hot air. So the buoyant force pushes it up. But the weird thing is that as it rises and expands, it actually starts to cool off. And why is that? I mean, I thought hot air was supposed to rise, so why does it cool as it expands and rises? Well, because as the particles expand, they recede from each other. They start moving away from each other. So they always have some velocity away from each other. That means when they collide, their relative speed versus each other is low. And when they bounce off each other, they actually slow down a lot. here's a little picture of it. You know, you've got this slow moving particle, but it's moving from left to right. Then you've got this fast moving particle moving from left to right. But from the fast moving particle's perspective, this guy's not going, this guy, because he's moving away from him, they're not coming together as fast as he's moving from our perspective. So when they collide, you know, there's less of an energy transfer. Well, I should say when they collide, there's less. This guy doesn't speed up as much as if the gas weren't expanding. So yeah, he loses energy and he doesn't gain as much. So overall, the net effect is that everything starts cooling down. And yeah, so what you see here is slower particles equals lower temperature, right? And so here's an example of an expanding gas. You see how everything is moving away from each other. And that's why this expansion reduces temperature. Okay, we have our first pair deck. So let's see